Section 23, Cosmic Inflation. There is physical evidence supporting the standard cosmological model back to the first second after the Big Bang, and even the first trillionth of a second. But there are some issues that we will now discuss. Astronomers believe our visible universe of galaxies seems nearly homogeneous and isotropic on a large scale today, greater than 100 megaparsecs. And the cosmic microwave background has the same temperature in all directions, to 10 parts per million. Working backward in time, the standard cosmological model says that energy density should have been even more isotropic in the early universe, with radiation-dominated decelerating expansion. However, the very early universe should have had quantum mechanical fluctuations in density and temperature that decelerating expansion should have amplified over time. If expansion was dominated by radiation since the Planck time, distant points in opposite directions should not have been in causal contact in the past, and our universe should be less isotropic than it seems to be on the largest scale. Our current observable universe was about 5.6 meters in diameter, 10 to the minus 33 seconds after the Big Bang or Planck time. But light could only have traveled less than a trillionth of a meter in that amount of time. So what happened to early quantum mechanical fluctuations in density and temperature? Why is the cosmic microwave background so isotropic? This is called the horizon problem. Secondly, our observable universe appears to be nearly flat, near zero curvature today, and should have been even closer to flat in the past, tending toward zero curvature at the Big Bang if radiation dominated expansion. A universe can have positive or negative curvature with any quantitative value. Why should our universe have the special value of zero curvature? If our universe had deviated a tiny bit more from flatness at the time of Big Bang nucleosynthesis, our universe would have ended long ago in a big crunch, or we'd have a big chill with no stars or galaxies and no life. Our universe seems to have a special condition for flatness to have lasted this long and produced stars and galaxies. This is called the flatness problem. Physicists have never found a particle with an isolated magnetic north pole or south pole, but believe these existed in the extremely early universe. This is called the magnetic monopole problem. In place of conditions for flatness, homogeneity, and magnetic monopoles, cosmologists propose that there was an extremely short period, extremely early in the universe, when expansion of the universe accelerated and the scale factor increased exponentially by a lot, by at least 26 orders of magnitude in one scenario. Cosmologists call this inflation, cosmic inflation, cosmological inflation, or hyperinflation. Cosmic inflation by at least 26 orders of magnitude in around 10 to the minus 33 seconds. This graph shows, for one scenario, the scale factor for the first trillionth of a second after the Big Bang. The horizontal scale is the logarithm of time in seconds since the Big Bang, from -50 on the left to -20 on the right. The vertical scale is the logarithm of the scale factor, from -60 at the bottom to -20 at the top. So 26 orders of magnitude of accelerating exponential expansion in 10 to the minus 33 seconds before the 26 orders of magnitude of decelerating expansion from the end of this inflation until dark energy became dominant. When radiation or matter dominates expansion and expansion is decelerating, the magnitude of curvature increases with time. But when expansion is accelerating and exponential, the magnitude of curvature decreases with time. Before inflation, here, space might have been quite curved, and perhaps destined for a big crunch, but the curvature became extremely diluted by the huge exponential inflation. So curvature now seems zero, or close to it. When inflation completed, what will become our observable universe was a sphere as small as 2.8 meters in radius, and all points within that sphere had previously been in causal contact and thermal equilibrium before inflation, which is why our cosmic microwave background is so uniform, and our observable universe is so uniform on the largest scale. Our universe might be spatially infinite or spatially finite, but if finite, its present size is at least 4 times larger than our observable universe, and possibly much, much larger. There are some inflation-related terms we will not cover: false vacuum and inflaton field. Radiation temperature falls with expansion, so why was our universe not extremely cold after cosmic inflation? Energy was added back to the radiation and matter in a process called cosmic reheating, such that the temperature was as hot after inflation as before. And we look back to see a hot Big Bang. Confusingly, some authors called the time of reheating the hot Big Bang, and the inflation was before the Big Bang. Cosmic inflation is speculative, so I tend to think of the end of reheating as effectively our hot Big Bang, but I don't like to say before the Big Bang, which is speculative. Switching back to the present, about 3.6 billion years ago, the matter and radiation energy density fell below the dark energy density, and since then, the dark energy density has dominated the expansion of the universe, which has been accelerating. In the future, expansion will approach an exponential function of time, and the scale factor will increase by a factor of 10 every 40 billion years. But in the extremely early universe, one scenario has the exponential expansion increasing the scale factor by a factor of 10 every 10 to the minus 34 seconds, less than a billionth of a trillionth of a trillionth of a second, and continue to increase the scale factor by at least 26 orders of magnitude. That was an amazing epoch of the expansion of the universe, if true. These amounts of time are too small for us to really appreciate, but there is a different way to look at this relative to the extremely small Planck time. If there was inflation, it may have started between 2 million and 200 million Planck times after the Big Bang. Then inflation continued for at least 100 times longer than the starting time. Then inflation ended, reheating occurred, and expansion went back to being dominated by radiation. So when inflation ended, the universe had been undergoing exponential inflation for 99% of its existence, if true. In the description of the YouTube video, I will give a link to an interesting article from Big Think. We cover more about the conditions in this early period in the next section.